You did the work. You trained hard this week, maybe harder than someone 20 years younger. You slept. You ate the right things. You put in the hours. And 3 days later, your body still isn't ready. The legs carry a deep, settled heaviness. Your joints talk to you in the morning before you've had your first cup of coffee. Your grip hasn't fully come back. And somewhere, quietly, in the part of your mind you don't share with anyone, a voice has started asking a question you haven't wanted to sit with. Every protocol on this channel is reviewed by a clinical pharmacist and researcher. All scientific references are in the description below. Here's the question nobody in the gym is asking. What if your slower recovery after 40 is not a failure of your body, but evidence that the biological rules of recovery have permanently, completely changed? Not declined. Changed. Because those are two very different situations. One calls for trying harder. The other calls for thinking differently. And here's what I want you to sit with, right now, before we go any further. What if the recovery protocol you've been following, the one that worked for years, is now working against you? Not a little. Under certain conditions, in specific biological circumstances, actively against you. That question doesn't have a quick answer. But by the time we're finished today, you will understand exactly what is happening at the cellular level. In your muscle tissue, in your bloodstream, in the mitochondria of every fiber you trained this week. And you will understand precisely why what worked at 25 is not just less effective now. The answer, when it comes, is going to change how you look at every session you've had for the last decade. And it starts in a place most people never look. Let's begin with what most people believe recovery actually is, because the gap between that belief and the biological reality is exactly where the problem lives. The conventional model goes like this. You train, you damage muscle fibers, you eat protein, you sleep, and your body repairs the damage and comes back slightly stronger. Rest more, eat more, repeat. That model is not wrong, but it describes only one layer of a process that, after 40, involves at least 4 or 5 distinct biological systems, all of which must coordinate precisely in a specific sequence for recovery to happen efficiently. And the conventional model completely ignores the layers that are failing. Let's walk through what recovery actually looks like at the molecular level, because once you see this clearly, you will never think about a rest day the same way. When you train hard enough to matter, when you generate the mechanical load that creates genuine myofibrillar disruption, your body initiates an inflammatory response within minutes. This is not optional, and it is not damage in the pathological sense. This acute, localized inflammation is the signal. It is your body saying, something happened here. Resources need to be deployed. In the first 2 hours after training, neutrophils, the first responders of your immune system, migrate into the stressed muscle tissue. They begin phagocytosing cellular debris, releasing enzymes that break down damaged proteins, and secreting cytokines, pro-inflammatory signaling molecules including IL-6, TNF-alpha, and IL-1 beta. These molecules function as a molecular distress call. They don't just communicate damage, they summon the machinery of repair. That machinery, in the context of muscle recovery, centers on a population of cells called satellite cells, also called myogenic stem cells. Satellite cells sit dormant along the surface of your muscle fibers in a state called quiescence. Under the microscope, they are essentially invisible, flat, quiet, waiting. When the inflammatory signal reaches them, they activate, proliferate, and ultimately fuse with damaged muscle fibers. They deposit new contractile proteins. They restore the architecture of the sarcomere, the fundamental functional unit of muscle contraction. This is how you rebuild. This is how adaptation actually happens. Now here is where the biology changes, quietly and profoundly, as you move through your 40s. The number of satellite cells in human skeletal muscle declines with age. That is a well-documented fact. But the decline in satellite cell number is not the most important part of the story, and most articles written on this subject stop there, which is why most recovery advice is built on an incomplete foundation. What matters more, and what the research has clarified with considerable precision over the last decade, is that the remaining satellite cells become less responsive to activation signals. They don't hear the call as clearly or as quickly. Their capacity to self-renew after activation is impaired. And critically, the biological environment in which those satellite cells are operating, the local tissue environment created by the inflammatory response, has changed in ways that compound every one of these deficits. This brings us to the central mechanism that explains your recovery slowdown at its most fundamental level. A pathway called mTORC1, the mechanistic target of rapamycin complex 1. mTORC1 is the master integrator of anabolic signaling in skeletal muscle. Think of it as the switch that, when activated, initiates the cascade of gene expression required to manufacture new muscle protein. mTORC1 responds to three primary inputs: mechanical load, the amino acid leucine, specifically leucine, and growth factors, principally IGF-1. When all three converge, mTORC1 activation is robust. Muscle protein synthesis rises, the repair process accelerates. In a younger body, this system is sensitive. A hard training session and a normal meal with adequate protein activate mTORC1 reliably. The spike in muscle protein synthesis is sharp. It sustains itself for 3 to 5 hours. And the net result, over the recovery period, is repair, consolidation, and adaptation. After 40, the sensitivity of this switch has changed. The scientific literature on this uses a specific and important term: anabolic resistance. What it means is that the same stimulus, the same training load, the same protein intake, produces a smaller, shorter, blunted mTORC1 response in an older body. The peak is lower, the duration is shorter. And that reduced window of elevated protein synthesis still has to accomplish the same amount of repair work, while operating against a biological background that is generating significant additional noise. Anabolic resistance is real. It is measurable in muscle biopsies, and it is the primary reason that the protein dose and training protocol that served you at 30 is now leaving adaptation on the table. But here is the part that the anabolic resistance explanation leaves out. There is a deeper mechanism underneath it, one that most physicians have never explained, because most physicians were not trained in the intersection of immunology, exercise physiology, and cellular biology, where this mechanism lives. It is a mechanism that explains specifically why the inflammation after your training sessions no longer resolves as cleanly as it used to, why you feel more beaten up on day 2 than day 1. Why that heavy, tender systemic fatigue is not just soreness. It is a signal, a very specific one. And what it's pointing to is going to change the entire picture of what's happening in your body and what to actually do about it. That deeper mechanism has a name that exists almost entirely outside mainstream health media. It is called inflammaging, and the reason you have probably never heard it explained with precision is that it occupies a strange middle ground between immunology, endocrinology, and exercise science. A space where very few clinicians spend professional time, but where the most consequential variables in aging-related performance decline actually live. Inflammaging. The term was introduced by immunologist Claudio Franceschi following population studies on centenarians, describes a state of chronic, low-grade sterile inflammation that accumulates across decades of cellular life. Not the acute, purposeful inflammation that your training triggers, and that resolves within days. This is different in kind, not just degree. This is a persistent, elevated baseline of inflammatory activity that exists in your bloodstream and in your tissues continuously. Not triggered by a specific event, not resolving after a specific intervention, and not visible in any standard blood panel unless someone is specifically looking for it. The molecular signature of inflammaging overlaps with the molecules of exercise-induced inflammation, IL-6, TNF-alpha, IL-1 beta, but the biological context is completely different. In acute post-training inflammation, these molecules are signaling damage and initiating repair in a specific location. In inflammaging, they are signaling a kind of diffuse, chronic cellular stress. They are not pointing to a repair site. They are background noise. And the effect of that background noise on the acute inflammatory process, triggered by training, is significant, specific, and almost never discussed in any fitness context. Here is the mechanism in precise terms. When you train at 45 or 50 and trigger the normal acute inflammatory response, That response is now initiating from an elevated baseline. The delta, the increase in cytokine signaling above resting level, is occurring in a system already primed. And in that context, the immune system's ability to do three critical things becomes compromised: to amplify the signal to the right level, to sustain it for the right duration, and, most critically, to resolve it completely. The resolution phase is where the failure is most consequential. And this is where most people feel the difference without having any language for it. Inflammatory resolution is not passive. It is not simply the inflammatory process burning out like a fire that runs out of fuel. Inflammation resolves actively through a class of molecules called specialized pro-resolving mediators, SPMs. These include 4 families of bioactive lipids: lipoxins, resolvins, protectins, and myrisins. The names matter less than the function. SPMs are the biological off switch for inflammation. They actively signal macrophages to switch from a pro-inflammatory to an anti-inflammatory phenotype, from tissue destruction mode to tissue repair and clearance mode. They promote the phagocytosis of cellular debris. They restore local homeostasis in the tissue. They do not suppress inflammation. They actively drive its resolution. And after 40, the production of specialized pro-resolving mediators declines. The biosynthetic pathways that produce them run through omega-3 fatty acid metabolism, specifically through the enzymatic conversion of EPA and DHA into their bioactive SPM products by enzymes called lipoxygenases and cyclooxygenases. As these pathways become less efficient with age, the body continues to generate the acute inflammatory signal from training, but the resolution signal grows quieter. The result is not simply more inflammation. It is slower, less complete, more prolonged resolution of the inflammatory response. And now the link to satellite cell function closes the loop. Satellite cell behavior during muscle repair is not governed only by the inflammatory signal that activates them. It is also governed by the resolution signals that coordinate their subsequent differentiation, the signals that tell them they are no longer in the debris clearing phase, that the tissue environment is ready for deposition of new contractile protein, that it is time to fuse and differentiate rather than continue proliferating. When SPM production is diminished and the resolution phase is delayed, satellite cells receive incomplete coordination signals. The repair process runs in a degraded environment. The assembly of new myofibrils is slower. The clearance of damaged tissue is incomplete. And the low-grade inflammatory milieu in the muscle persists longer, directly impairing the anabolic signaling that mTOR1 depends on to drive protein synthesis. This is why your recovery is slower, not in a general sense. In a specific, mechanistically defined sense. Your inflammatory resolution pathway is running below its designed capacity, and that one deficit cascades through every subsequent step in the repair sequence. Which means we now have to ask what else is cascading. Because Inflammaging and SPM decline explain the resolution problem. But there is a second major system failing simultaneously, and it operates in a completely different biological domain. The second mechanism is hormonal, but not in the way the standard conversation about testosterone and aging frames it. And this is where that conversation consistently misses what matters. Yes, testosterone declines with age. Approximately 1% per year after 30 in men, with more variable but significant declines in women related to the peri- and postmenopausal hormonal transition. Yes, that reduction has real effects on muscle protein synthesis, on satellite cell activity, on motivation, and on the psychological factors that govern training consistency. None of that is fabricated. But testosterone, in the context of post-exercise recovery, is not the primary driver of the impairment after 40. It is one instrument in a complex hormonal orchestra. And the instruments that are most out of tune are not the ones most people are watching. Let's start with insulin-like growth factor 1, IGF-1. IGF-1 is produced primarily in the liver in response to growth hormone signaling, and it is the most potent direct anabolic signal in skeletal muscle tissue. It acts directly on mTOR1, driving protein synthesis. It directly activates satellite cells. It suppresses myostatin, the negative regulator of muscle growth. And it has a locally produced isoform called mechano-growth factor, or MGF, that is synthesized within muscle tissue itself in response to mechanical loading. Specifically, in response to the stretch and tension of training. MGF is the immediate, local activator that gets satellite cells out of quiescence and into the active repair process. It is the first signal in the satellite cell activation sequence. After 40, total circulating IGF-1 declines significantly, typically by 30 to 40% between the ages of 30 and 60 in both sexes. Growth hormone pulse amplitude decreases. The liver's sensitivity to GH signaling diminishes, and the local production of mechano-growth factor within muscle tissue, the isoform doing the most critical immediate work, is particularly vulnerable to the hormonal environment and to the inflammatory background we discussed in Block 3. In a tissue environment already elevated by inflammaging, MGF production following a training session is blunted. Satellite cells receive a weaker, later activation signal. The repair window shifts backward in time. Now, here is the hormonal interaction that most clinicians and most fitness professionals miss entirely. And it requires understanding cortisol not as a stress villain, the way it is usually presented, but as a metabolic regulator with a very specific and important antagonistic relationship to the recovery process. Cortisol is catabolic. It activates gluconeogenesis, the breakdown of amino acids for glucose production. It suppresses mTOR signaling. It inhibits satellite cell proliferation, and it directly counteracts the anabolic effects of testosterone, IGF-1, and growth hormone at the receptor level. Cortisol does all of this by design. In appropriate contexts, these are important physiological functions. The problem after 40 is not that cortisol exists, or even that it rises after training. The problem is the kinetics of its clearance. In a younger body, the post-training cortisol spike, which is real and appropriate, is brief. Cortisol rises, performs its metabolic function in the immediate post-exercise period, and is cleared rapidly. The cortisol-to-testosterone ratio returns to its anabolic baseline within a few hours. In an older body, cortisol clearance is slower. The half-life of cortisol in the tissue is effectively extended. The cortisol-to-testosterone ratio remains elevated for a significantly longer window after training. And during that window, the hours when cortisol is still high and the anabolic hormones have not yet re-established their dominance, the muscle is in a net catabolic state. mTOR signaling is partially suppressed. Satellite cell proliferation is slowed. And the protein synthesis process that should be building on the training stimulus is instead partially countered by a hormonal environment that hasn't finished clearing from the session. Clinical research has confirmed this pattern consistently. Studies measuring hormonal recovery kinetics in subjects over 40 performing identical resistance training protocols to younger subjects show that the cortisol-to-testosterone ratio remains elevated significantly longer in the older group. The net anabolic window, the period after training during which the hormonal environment favors repair and growth, is compressed. The recovery debt that accumulates when that window is mismanaged is real and measurable. You have felt this, even if you didn't have the language for it. A good, productive training session where you felt capable, even strong, followed 2 days later by a level of systemic fatigue that didn't match what you did. Cognitive blunting. Heaviness that felt different from muscle soreness. More global, more metabolic. That is a prolonged cortisol exposure in a hormonal environment that cannot counterbalance it with the speed it once could. This is also why training volume and frequency, the variables that worked precisely at 30, require recalibration at 40 and beyond. Not because you are getting weaker, not because you need to train less, because the hormonal recovery dynamics have shifted in ways that are concrete, measurable, and, here is the critical word, manageable, if you understand the mechanism. But there is a third layer to this that operates not in the bloodstream, not in the signaling molecules, but inside the cell itself, at the level of the structures that produce every unit of energy your body uses to repair, rebuild, and adapt. And what is happening there changes everything about why effort alone stops being sufficient. Your mitochondria are not energy factories. That framing is accurate but criminally reductive for what we need to understand now. Your mitochondria are quality control nodes. They are the cellular infrastructure that determines not just how much energy is available for recovery, but whether the cellular environment in which recovery is happening is clean, functional, and capable of executing the repair sequence from start to finish. During and after training, your mitochondria are simultaneously doing three things that are directly relevant to what happens in the recovery window. First, they are generating ATP, the chemical fuel that powers every active process in muscle repair, including protein synthesis, satellite cell proliferation, and membrane restoration. Second, they are generating reactive oxygen species, ROS, as an unavoidable byproduct of electron transport chain activity. At moderate, controlled levels, ROS serve as intracellular signaling molecules. They activate heat shock proteins, they signal the upregulation of antioxidant defenses, and they contribute to the acute adaptive response to training. At high levels, they oxidize lipids, proteins, and DNA, creating the kind of cellular damage that initiates repair cascades of their own. Third, your mitochondria are continuously engaged in a process of self-monitoring and self-renewal called mitophagy. The selective identification and clearance of damaged or dysfunctional mitochondrial subunits, ensuring that the mitochondrial network maintains its structural and functional integrity. After 40, all three of these functions are compromised, and they compound one another in a way that creates a biological environment progressively less suited to efficient recovery. Let's start with mitochondrial efficiency. The proteins that form the electron transport chain, the 5 major complexes of the inner mitochondrial membrane, accumulate structural damage over decades of oxidative exposure. This damage reduces their efficiency. Fewer electrons are passed cleanly through the chain. More electrons leak and react with oxygen to form superoxide, the primary precursor of intracellular ROS. The result is a system that consumes more oxygen, produces less ATP, and generates more oxidative byproducts simultaneously. Less energy available for repair, more oxidative burden in the tissue, and a cellular environment that is harder to clean up after each training session. Now add the mitophagy failure. The clearance of damaged mitochondria depends on a regulatory protein called PINK1, PTN-induced kinase 1. PINK1 accumulates specifically on the surface of mitochondria that have lost their membrane potential, the electrochemical gradient that healthy mitochondria maintain. When PINK1 accumulates, it recruits a protein called parkin, which initiates the ubiquitination and autophagic degradation of the damaged mitochondrion. This is how your cells normally prevent mitochondrial damage from becoming permanent. After 40, PINK1 activity declines, parkin recruitment is slower, and the efficiency of mitophagy as a whole is reduced. Damaged mitochondria are not cleared at the rate they accumulate. They persist in the cell. They continue generating excess ROS. They continue degrading ATP production. And they begin triggering a cellular response that has profound implications for the entire recovery landscape. That response is cellular senescence. A senescent cell is not a dead cell. It is a cell that has stopped dividing, permanently, in response to a damage signal it cannot repair. In the context of mitochondrial dysfunction, the damage signal runs through 2 tumor suppressor pathways, p53 and p21. When mitochondrial damage reaches a threshold that the cell's repair machinery cannot resolve, p53 activates p21, which permanently arrests the cell cycle. The cell enters a state of growth arrest from which it cannot exit, but it remains metabolically active. And what it secretes in this state? A complex mixture of pro-inflammatory cytokines, matrix metalloproteinases, and growth regulatory factors is called the senescence-associated secretory phenotype, the SASP. Senescent cells with active SASP are not passive bystanders in your muscle tissue. They are active disruptors. Their secretions amplify the chronic inflammatory background, directly feeding the inflammaging process we discussed in Block 3. Their proteases degrade extracellular matrix proteins needed for tissue structure. Their inflammatory signaling directly impairs the function of neighboring satellite cells. inhibiting their activation and their ability to differentiate into new muscle fiber. The accumulation of senescent cells in skeletal muscle increases progressively through the 40s and 50s. It is not uniform across individuals. It is modulated by training history, nutritional status, sleep quality, and a number of other factors we will return to in the protocol. But the trajectory, in the absence of intervention, is consistent. And now the picture becomes visible in its full complexity. Mitochondrial dysfunction generates excess ROS, which impairs satellite cell function and contributes to cellular senescence. Senescent cells amplify inflammaging through SASP secretion. Inflammaging impairs SPM production and delays inflammatory resolution. Delayed resolution degrades the satellite cell coordination signals for repair. Cortisol clearance is slow, blunting the anabolic window that muscle protein synthesis depends on. And anabolic resistance means that even when the window is open, the stimulus required to activate mTOR-1 effectively is now higher than the standard protocol delivers. This is not a single failure. This is a failure of synchrony. 5 systems drifting slightly out of phase with one another, each impairment feeding the next, until the cumulative deficit becomes impossible to ignore and impossible to brute force through. Everything we have just covered now points to one specific practical conclusion, and the conclusion is not what most people expect. Let's hold all of it together, because there is a pattern in these 3 layers that only becomes visible when you step back far enough to see them as an integrated system. Your muscle recovery after 40 operates through a biological sequence. A training stimulus creates controlled mechanical stress and triggers the inflammatory initiation signal. That signal must amplify to the right level to activate satellite cells and recruit immune support, but not so far above the chronic inflammatory baseline that the resolution process is overwhelmed before it begins. The acute inflammatory phase must then resolve completely through SPM activity, allowing satellite cells to shift from proliferation to differentiation, depositing new contractile protein and restoring fiber architecture. During and after that repair sequence, the hormonal environment must be net anabolic, cortisol cleared, testosterone and IGF-1 reasserted, to allow the newly synthesized tissue to consolidate rather than be broken down. And throughout the entire window, the mitochondria within the recovering muscle cells must produce sufficient ATP to power every active process, clear their own accumulated damage through mitophagy, and not generate enough oxidative stress to trigger senescent cell formation in the neighboring tissue. After 40, every single link in that chain is under pressure, not broken, under pressure, in ways that are specific, measurable, and targetable. The inflammatory initiation signal fires, but from a higher chronic baseline, so the acute response blends into the background noise. The SPM production needed for clean resolution is declining, so the resolution phase runs slower, longer, and less completely than it should. The mechano-growth factor signal that activates satellite cells is blunted in the early hours after training, so the repair workforce assembles later than it needs to. The cortisol-to-testosterone ratio stays elevated longer, compressing the net anabolic window at precisely the time when satellite cells are trying to differentiate and new protein should be consolidating. And the mitochondria coordinating all of this energy production are less efficient, accumulating damage faster than mitophagy can clear it, contributing to a slowly growing population of senescent cells that amplify the inflammatory background that made resolution difficult in the first place. The circle closes on itself, and it closes in a direction that, without intervention, moves progressively toward greater recovery impairment, not less. I want to give you an analogy, because this system is complex enough that abstraction risks losing it. Think of your recovery biology as a symphony orchestra. Each mechanism we've discussed is a section: strings, brass, woodwinds, percussion. When you are young, the conductor has full authority. Every section reads the same score. The tempo holds. Each movement resolves cleanly, and by the time the next piece begins, the orchestra is rested, tuned, and ready. After 40, the conductor is still present. The score hasn't changed, but the timpani section, your mitochondria, has been running slightly behind the beat for years. Not noticeably, not enough to stop a performance, but enough to accumulate a lag. The brass, Your pro-inflammatory signaling has started playing louder than the score calls for, because the conductor's correction signal is delayed. And the strings, your specialized pro-resolving mediators, the resolution machinery, have gotten progressively quieter, not because the musicians are gone, but because the chairs are fewer and the instruments less resonant than they were. The piece still plays, the orchestra still performs, but it doesn't resolve cleanly at the end of each movement. There is residual sound where there should be silence, and if you keep asking the orchestra to perform more frequently, at higher intensity, without addressing the internal timing issues, the output gets worse, not better. Regardless of how much the musicians try. What changes this is not asking the musicians to try harder. It is not adding more rehearsals. It is understanding which sections have drifted from tempo and intervening precisely, with the right instrument, at the right moment in the score. That is the logic that governs the protocol in the final segment, not general recovery recommendations. Not advice calibrated for a 25-year-old body running on a different set of biological rules. A specific, sequenced, mechanism-targeted approach, built around exactly the biological reality we have just spent 2 segments establishing together. Not what to do in general. Exactly what to do. Exactly when. And why the sequence, the order in which these interventions are applied, matters more than any individual component. Everything we've covered, the impaired SPM production, the blunted mechano-growth factor signal, the cortisol-to-testosterone imbalance, the mitochondrial efficiency loss, the senescent cell accumulation. All of it has been pointing toward a single practical question. What do you actually do with this information? And here is where precision becomes everything. Because the standard recovery advice that populates the fitness and health space is not wrong. Rest more, eat more protein, sleep better. Those are not bad recommendations, but they operate at the wrong level of specificity. They are designed for the generic model of muscle recovery, damage, inflammation, repair, without accounting for the biological environment in which that process is now running. Advice built for a 25-year-old physiological template, applied to a 45-year-old biological system, will always underperform. Not because the person is doing it wrong, because the template is wrong. The organizing principle of what follows is this. You are not trying to force recovery to happen faster. You are removing the specific biological obstacles that are preventing your natural recovery process from running at its designed efficiency. That is a different intervention logic. It targets the bottlenecks. It works with the biology rather than against it. And it requires understanding which bottlenecks matter most, which is exactly what the last 2 segments have established. The first principle, timing, and not the timing most people are thinking about. The conventional conversation centers on the post-workout anabolic window. Eat protein within 30 to 60 minutes, spike leucine, activate mTOR. That advice is based on real science, but it is incomplete in a way that matters profoundly after 40. Research on anabolic resistance, including randomized controlled trials specifically enrolling subjects over 40, shows that the mTOR-Ki1 activation threshold is meaningfully higher in older muscle. The leucine concentration in the bloodstream that would reliably activate mTOR-Ki1 in a younger subject does not reliably cross the threshold in an older one. The receptor sensitivity has shifted. You need a higher leucine signal, more precisely timed, with fewer competing amino acids in the absorption window. And because leucine concentration in the blood is determined not just by how much protein you eat, but by how fast that protein is absorbed, the source of the protein and the dose at which it's taken both matter far more than they did before. This is also why the timing of recovery interventions matters beyond just the immediate post-training window. The recovery process after 40 extends further into the subsequent hours and days than it does in younger athletes. The residual inflammatory activity, the slower satellite cell activation, the compressed anabolic window, all of these mean that what you do in the full 48 to 72 hours between sessions is as consequential as what you do in the first 30 minutes after training ends. The recovery window after 40 is not just the hour after training. It is the entire interval between sessions. And managing that interval, systematically, with intention, in a sequence that targets the specific mechanisms that are failing, is what separates people who feel progressively diminished by training from people who feel progressively refined by it. Before we go into the specific interventions, if you have stayed with this video to this point, you are exactly the person this channel was built for. We are approaching a milestone that matters to us, and if you haven't subscribed yet, that one action makes a real difference. Every protocol on this channel is reviewed by a clinical pharmacist and researcher. There are no sponsors influencing what gets recommended here. No algorithm-driven shortcuts, just the science, translated precisely into what it means for your body, your decade, and your goals. Subscribe if you haven't. It takes a second. And now, let's build this protocol. Because here's what almost every well-intentioned recovery program gets wrong. They address the what without the when, and the what without the why, and the interventions individually without understanding how they interact. The protocol that follows addresses all three: 4 domains, a specific sequence, and the mechanism behind every element. Domain 1, protein architecture and the leucine threshold. The foundational intervention, and the one most people are already attempting, but in a way that leaves the majority of the biological benefit unrealized. After 40, the leucine threshold for mTOR C1 activation has been established by multiple research groups, most notably from Stuart Phillips' laboratory at McMaster University and Luc van Loon's group at Maastricht, to be approximately 5 to 3 grams of free leucine per feeding. In a younger adult, the threshold sits around 7 to 2 grams. That difference, roughly a gram of leucine, translates directly to protein dose. A standard 25-gram serving of whey protein, which contains approximately 10% leucine by weight, delivers around 5 grams of leucine, marginal for a younger adult, potentially sub-threshold for you. Immediate post-training: 40 to 45 grams of a fast-absorbing high-leucine protein source, consumed within 45 minutes of training. Whey protein isolate is the most efficient choice. 10% leucine by weight means 40 grams delivers a confirmed 4 grams of leucine, reliably crossing the mTOR C1 activation threshold. If you are using plant-based protein, combine a leucine-enriched pea protein with supplemental free-form leucine to reach 5 grams total. The 45-minute timing is not arbitrary. The post-training cortisol environment is still elevated, and leucine-driven mTOR activation partially attenuates the catabolic signal during this window. 3 to 4 hours later, not 1 hour, 4 hours, a second protein feeding of 30 to 40 grams from a slower digesting source. Casein protein, Greek yogurt, cottage cheese, whole eggs. This second pulse takes advantage of a recovery characteristic that is documented in older trained adults but rarely discussed. Muscle protein synthesis in this population can remain meaningfully responsive to amino acid availability for 5 to 6 hours post-training, significantly longer than was assumed under the older, narrower anabolic window model. You are not missing a window. You are populating a longer one. 60 minutes before sleep. 30 to 40 grams of casein protein. Van Loon's group has demonstrated in controlled trials that pre-sleep casein supplementation in older adults increases overnight muscle protein synthesis by approximately 22% compared to placebo conditions. The mechanism matters. Growth hormone, your primary hormonal driver of overnight tissue repair, is secreted in pulses during slow-wave sleep. Having bioavailable amino acids present during those GH pulses allows the anabolic signal to be matched with its substrate. This is not a convenience recommendation. It is timed to the most important hormonal event in the recovery cycle. Domain 2, inflammation resolution, supporting SPM production. The target here is the resolution deficit we established in Block 3. This is not anti-inflammatory intervention. Suppressing the acute inflammatory response to training would impair adaptation. This is pro-resolution intervention, providing the biological raw materials that allow the resolution phase to run at the efficiency it would run at in a younger, well-nourished system. The primary intervention is omega-3 fatty acid supplementation at therapeutic rather than cardiovascular dosing. EPA and DHA, the marine-derived long-chain omega-3s, are the direct precursors to the SPM families. Resolvins, protectins, and maricins are synthesized from EPA and DHA through enzymatic pathways that become less efficient with age. Supplementing the precursor load does not fully compensate for the enzymatic decline, but it meaningfully shifts the production balance in the right direction. The dose: 3 to 4 grams of combined EPA plus DHA per day. This is higher than standard cardiovascular recommendations. Most commercial fish oil capsules contain 300 milligrams of combined EPA-DHA. You need a high-concentration formulation, a pharmaceutical-grade fish oil delivering 1 gram of combined EPA-DHA per capsule, or an equivalent algae-derived DHA plus EPA product. Take this daily, not only on training days. The SPM biosynthetic pathway requires consistent precursor availability. Intermittent supplementation does not maintain the pathway efficiency. Timing note: taking your omega-3 dose 2 to 3 hours after training, during the peak of the acute inflammatory phase, provides precursor availability at the precise moment SPM synthesis would naturally be most active in a younger system. Domain 3: Mitochondrial function and cellular quality. 2 interventions with the strongest evidence base for the over 40 athlete at the mitochondrial level. First, creatine monohydrate, 5 grams daily, taken consistently regardless of training schedule. No loading phase is necessary. Steady-state tissue saturation is achieved in 3 to 4 weeks and maintained with daily dosing. The recovery rationale for creatine in older adults extends beyond its well-known role in rapid ATP resynthesis. Multiple controlled trials have shown that creatine supplementation in this population reduces post-training markers of oxidative stress, decreases plasma creatine kinase elevation, the enzyme marker of muscle membrane damage, after intense exercise, and in several trials directly reduces the severity and duration of delayed onset muscle soreness at 48 hours. The mechanism involves both reduced membrane fragility and a direct antioxidant buffering effect within the muscle cell. This is one of the most evidence-supported interventions in the entire recovery literature for adults over 40. It is not a supplement for young athletes. The evidence base for older adults may be stronger. Second, NAD plus precursor supplementation targeting the AMPK-SIRT1 PGC1 alpha axis, the master regulatory pathway governing mitochondrial biogenesis and mitophagy efficiency. NAD plus, nicotinamide adenine dinucleotide, is the cofactor required by SIRT1, the deacetylase enzyme that activates PGC1 alpha, which in turn drives both the formation of new mitochondria and the upregulation of the mitophagy machinery that clears damaged ones. NAD plus levels decline by approximately 50% between the ages of 20 and 60 across most tissues. Restoring NAD plus availability provides the mitophagy system with the cofactor it needs to function. The accessible intervention, nicotinamide riboside at 250 to 300 milligrams per day, or NMN, nicotinamide mononucleotide, at 500 milligrams per day, combined with resveratrol at 250 milligrams, taken alongside a fat-containing meal for absorption. Resveratrol activates SIRT1 directly, making it synergistic with NAD plus precursor supplementation. One provides the cofactor, the other activates the enzyme that uses it. The evidence base for these compounds in human subjects is developing, not definitive. But the mechanistic rationale is solid, the safety profile is well characterized, and the convergence of the cellular aging data is compelling. Every protocol on this channel is reviewed by a clinical pharmacist and researcher, because precision here is not optional. Domain 4, sleep architecture and the anabolic window. The final domain, and the one most people treat as general wellness advice rather than as a precision recovery intervention with specific mechanistic targets. The slow-wave sleep phase, stages 3 and 4 of the NREM cycle, is the window in which growth hormone secretion is most concentrated, in which cortisol is at its biological nadir, and in which the hormonal environment is most favorable for tissue repair and protein consolidation. After 40, the proportion of total sleep time spent in slow-wave sleep declines significantly. Adults in their mid-50s typically achieve 30 to 50% less slow-wave sleep than they did in their 20s. The growth hormone pulse during this phase is smaller, the repair window is compressed, and the cortisol nadir, the period of maximal hormonal favorability, is shortened. 2 specific interventions: sleep timing and magnesium glycinate. Sleep timing: a minimum of 7.5 hours in bed on training nights, with sleep onset before 11 p.m. The rationale is physiological, not conventional. Cortisol begins rising steeply around 3 to 4 a.m. regardless of when you fall asleep. This is a fixed feature of the circadian cortisol rhythm. If you sleep at midnight and wake at 7, cortisol is already rising through the last 90 minutes of your sleep, compressing the slow-wave window from the front. If you sleep at 10:30 and wake at 6, you protect more of the architecture. The slow-wave phase is front-loaded in the night. You get more of it in the first 2 to 3 sleep cycles. Protecting those cycles by sleeping early is not a sleep hygiene platitude. It is a recovery intervention with a direct mechanistic rationale. Magnesium glycinate: 200 to 400 milligrams taken 60 minutes before sleep onset. The glycinate chelate form crosses the blood-brain barrier efficiently and reduces neural excitability, specifically the excitatory glutamate, signaling that fragments slow-wave sleep architecture in the 40-plus adult. Multiple controlled trials show increased slow-wave sleep duration and reduced overnight cortisol exposure with magnesium supplementation in this population. This is not a sedative. It does not shorten sleep latency significantly in people who don't have sleep onset problems. What it does is allow the sleep architecture that is already trying to run to complete its natural pattern more fully. That distinction matters because the mechanism, slow-wave sleep restoration, is exactly the target we need. These 4 domains, applied in sequence with the timing rationale understood, address every major biological obstacle to recovery we have identified. Not generically, specifically. At the beginning of this, I asked you a question, and I left it unanswered deliberately, because the answer without the context is just a thought. The answer with everything we've now covered is something you can actually use. The question was, is your slower recovery after 40 a failure, or a signal that the rules have permanently changed? Here is the answer. It is a signal. Specifically, the signal that your biological system for repair has shifted into a different operating mode, one with a different set of requirements, a different set of bottlenecks, and a fundamentally different response curve to effort. The satellite cells are still there. The mTOR pathway still responds. The mitochondria still generate energy. The body still wants to rebuild. The impulse to repair, the biological will of the tissue to restore itself, has not diminished. What has changed is the precision required to support it. At 25, the system had enough redundancy and sensitivity that effort alone could carry it. Eat enough protein, sleep enough, train hard enough, and the biology compensated for the imprecision. The system was forgiving. After 40, that forgiveness has been withdrawn. Not as punishment, as physics. The margins are tighter, the thresholds are higher, and the sequencing between biological events, resolution before synthesis, hormonal clearance before anabolic consolidation, mitochondrial quality before energetic capacity, matters in ways that it simply didn't have to matter before. The person who understood this before today was training with the wrong clock. The protein came at the right time for 25, not 45. The sessions were structured for a hormonal clearance rate that no longer applies. The sleep was adequate in duration, but not protected at the timing that preserves slow-wave architecture. And the inflammatory residue from each session was accumulating, slightly, imperfectly resolved, session by session, until the body started carrying the weight of every training debt it had never fully settled. Understanding the mechanism does something that effort never could. It removes the confusion. It replaces the self-criticism, the quiet suspicion that you are somehow failing at something other people manage without difficulty, with a map. A clear, specific, mechanistically grounded map of exactly where the biology broke from its previous behavior, and exactly what is needed to work with it now. You are not losing something. You are navigating different terrain. Terrain that rewards precision in ways that brute force never will. And the people who perform at 60 the way most people perform at 40, the ones who seem to have found something that most haven't, are not genetic outliers. They are not on inaccessible interventions. They have simply understood the mechanism early enough, and applied the correct sequence consistently enough that the biological landscape has worked with them rather than against them. That is available to you. It has always been available. You simply needed the map. If this video gave you something, a piece of clarity you've been searching for, a mechanism you recognized in your own body, an answer to a question you hadn't been able to articulate, share it with 5 people over 40 who need it. Not as a favor to this channel. As a genuine act of generosity toward people who may be carrying the same confusion you walked in here with, and who haven't found this conversation yet. Leave a comment below. Tell me what you recognized. Tell me which mechanism resonated most, or which symptom you've been living with that now has a name. And tell me what you want this depth of treatment applied to next. Because this channel is built on those conversations, and the topics that come from your questions are consistently the most important ones. Follow for daily content. Because part 2 of this series goes somewhere specific and consequential. Sleep architecture as a precision recovery tool, the current data on peptide science for tissue repair, and what the research on BPC 157 and TB 500 actually shows for the over 40 body. That video exists because you watched this one. There is an old idea in physiology, deceptively simple, carrying more truth than it first appears. The body doesn't adapt to the training you do. It adapts to the training you recover from. Everything else is just an expensive way to get tired.